areas will cool off even though the planet overall is heating. Today what I'd like to do is explain how it is that humans change temperature. And I'll show you all the science you need. Very straightforward and it's simple. The best analogy is this one. What happens to the temperature of a parked car when you roll up the windows? Yes?
It's hotter.
It gets hotter. Can anybody please explain to me how rolling up the windows makes a car hotter? Yes? It traps the heat inside and cannot escape. Okay, what heat? Where did that come from?
Your body.
Light from the sun was absorbed by the car's interior. And the car's interior radiates that heat back to the interior, back to the airspace of the car. The windows being rolled up will trap that heat. This is quite simply the greenhouse effect. This is also how my greenhouse works. Anybody here in period 0? Gabe used to be, Julia used to be. Before they wimped out, we had some kids in this room in period 0. And anybody else is welcome to come see the facility. The greenhouse there is just like your car parked on a parking lot on a sunny day. Please look up. Sunlight comes from the sun. Some amount of sunlight bounces off. Other sunlight goes through the glass, is absorbed by the stuff on the inside, and that stuff gives off heat, transformation of energy. That heat that's filling up the space, some of it will leave, some of it stays inside. The stuff that leaves doesn't affect the temperature. The stuff that stays inside raises the temperature. And speaking of period 0, would anybody like to have some delicious green peas picked this morning? Snap peas, sugar snaps, and sweet peas?
I was class.
Fine. It was pretty darn dark, yeah.
Okay.
Pass it that way, I guess. All right. So, here it comes like a greenhouse. I'll let you know which parts are noteworthy. First of all, you have to add a vocabulary term. That vocabulary term is albedo, A-L-B-E-D-O. I think Aaron wanted some.
Would you like more? Did you get none there? Thanks.
Albedo.
Albedo.
Albedo is also known as reflectivity. Which means how shiny something is. If you've got it. I guess this is number 20. Albedo is reflectivity. You know how some cars have that like shiny metallic window tint? It's all nice and shady on the inside because all the light is bounced outside so the inside doesn't get hot. Okay, that's raising the albedo of your car. Technically, if you wax your car, it cools it off a little bit because it's a little shinier. So less energy is absorbed, more of it's bounced away. That's albedo. Ice has a high albedo because it's shiny, reflective. Water and dirt have low albedo because they're dark and they absorb sunlight. Anybody have any questions about albedo? Our planet has shiny stuff like clouds, like dust in the atmosphere, and like ice on land. So our planet bounces off 30% of incoming sunlight. The other 70 is absorbed. You have to know those numbers. Here it comes. Of 100% incoming, 30 is reflected and 70 is absorbed. Mm-hmm.
So is the temperature heating up because the sunlight that's being reflected is now being trapped or more than absorbed?
Okay. Now, 30% is reflected away, 70% is absorbed, and that becomes heat. There are two ways our planet is getting hotter. One way is albedo goes down. You know, when we lose sea ice, our planet absorbs more energy from the sun. So for one thing, we're letting more light into the system. We've lowered albedo. For another thing, when that heat is trying to leave, we've raised the windows. So we're keeping more of the heat in. Because we have these things called greenhouse gases. Now, you might want to pay attention. This is probably the only time you'll ever see me dance. I'm not really going to dance. We'll talk later about greenhouse gases. You'll notice, please look up, they're all compound gases, meaning they all have parts. So, H1, H2, and O. H2O. Got that? Water molecule? Everybody like my water molecule? When you make this thing hot, these bonds right here, they become less stable. Because heat is energy. When you add energy to a compound, it will wobble. Technically, there's different types of wobble. Forgive me, I've forgotten the terminology, but there's this type of wobble, there's this type of wobble, there's this type of wobble, and there's this type of wobble. I think that there are others too. If you take a chemistry class, you'll learn about those one day. It's got something to do with the strength of the bond strength, and how much energy you've added. Thank you, yes, like that. Got me feeling the flow. But watch, this explains greenhouse gases. When you heat them up, they absorb that heat because their bonds become unstable. And then, watch me, those bonds, they like to come back to their original shape. And when they do that, they give the heat off again. Heat storage, greenhouse gases, they trap the heat. You see, if you're on Mars, you still have incoming radiation. Mars receives 100% of the sunlight. No atmosphere to block it. Zero albedo. So Mars has 100% coming in. It still becomes heat, but then, listen carefully, on Mars that heat just goes out to space. 100% in, 100% out. At 4 in the afternoon on Mars, the surface temperature on the sunny side is 300 degrees. Give or take a couple. Really effing hot. On the opposite side, on the dark side, the temperature is 200 below zero. 100% comes in, 100% becomes heat, and nothing can trap it. There's no gases. On Earth, that heat excites the water, and then later on that water goes, and it goes like this. This is the water molecule. Some of that heat continues on its way out to space, but some of that heat comes back to the Earth. Greenhouse gases. You have a heat arrow going out, the wobble, and then when it stabilizes, some of that comes back, and some of it goes out to the atmosphere. Greenhouse gas. When we add more gases, it's like we're rolling up the window on a parked car, making it just a little bit warmer. Or we're closing the vent on a greenhouse, keeping just a little bit more of the heat. More of the gases that wobble means more gases to put a little heat back down toward us. Without those gases, it would all just go out to space. We're not making more heat, we're just keeping more. Technically, with less albedo, we are making a little more heat, but not much. All the greenhouse gases are going up except water. All the greenhouse gases that humans can make, they're all going upward. None of them are going downward. So, here comes a little review of the science. You're going to love this. And I got to remind you, there's nothing uncertain about the parts I'm going to say. Now look, I am excited about the debate over what we do. I agree. I'm not sure if we should sacrifice American economic growth to stop climate change. That's not answered. That's debatable. That's an important conversation to have. Whether we should make other countries pay, whether we should pay, whether we should all take a hit together, whether we should take a turn losing some while all the other countries catch up. I don't know. A lot of ways to talk about this. How we fix it, how much we fix it, how much we're worried, what's going to happen in the future. But there's a few things that nobody can dispute. The basic thing about humans rolling up the window and making the planet hotter, settled. No-brainer. If anybody says they quote-unquote don't believe it, just say yes, but which part of the evidence is wrong? Just to show me where I'm wrong. Because you can say you don't believe in house cats, that doesn't mean you're accurate. Like if it's not a house cat, convince me, and you're right. But you can't disbelieve, and that somehow changes the facts of it being a house cat. If you're like, no, look, it's a dog wearing a costume, then it's like, you were right, and I was wrong. Correct me. But if you just don't believe in things that are, your lack of belief just makes you ignorant. Not right. And by the way, remember that some people already believe it. Okay. First of all, this was the first person to notice that our planet has an unusual weather pattern, climate pattern, excuse me. He did this at a time when they couldn't take his picture because it was a long, long time ago. The greenhouse effect, the idea that our planet traps some of the heat, this goes back almost 200 years now. And his name is kind of, the only people that know his name are like people who are serious science nerds. In the history of science, this guy turns out to have been really important, but we don't really talk about him anymore. And this guy made the first experiments to start looking at variables in the greenhouse effect back in roughly the time of Charles Darwin. Very famous earth scientist and naturalist. He has a beak and a creek named after him in the Sierras, Tyndall Peak and Tyndall Creek. I love his beard. No, it's like a jawline beard.
You should do that.
Yeah, there was a time, pre-hipster. Now look at the science apparatus that he was using. If that looks suspiciously hokey, you should realize that all scientific apparatus back then was all homemade. There wasn't like a company where you could mail order it. So he made his own experimental stuff to do the experiments. And he noticed something really simple. Watch me. If you put a given amount of energy into a blend of gases, the gases will heat up more if they have CO2 and methane and nitrous oxide and others. Tyndall figured out how much greenhouse gases heat up, how much heat they hold. So he would change the composition of the atmosphere with this, and then he would look at the temperature inside that atmosphere given a certain input of calories. In 1959, this guy did the math. He's like, if we all throw a coin into the ocean, that's not a lot. But if everybody throws 1,000 coins and there's a lot of people, won't that eventually fill up the ocean? But the math wasn't about coins in the ocean. It was about CO2 in the atmosphere. He said, look, we're all using coal. We're all using gasoline. We're starting to use natural gas. And there's a lot of people on the planet. And he just did the math. So he did like number of people times energy per person times energy growth per person. And he said, it's a really big atmosphere, but I think that there's enough people using enough energy to change the composition of the atmosphere. He wrote the first article that connected climate to fossil fuels in the 1950s, in 59. But before I was born, my mom was like 5 years old. Your parents might not have been born yet. And they already had, like in a public, like in the New York Times, like this isn't just scientific journals, this is like in the public media connections. This guy's name is Charles Keeling, and he was given the opportunity to put a CO2 sniffer on top of the big island of Hawaii on Mauna Loa. There's a big observatory up there. And apparently that's a really good place to measure the global atmosphere because it's not subject to human intervention. It's in the middle of the ocean at high altitude. It's got like the cleanest access to the atmosphere of any place you can drive to. Does that make sense? So he went up there and he started to measure CO2. He did that until his death, and then his students kept going. And you'll notice there's a pretty obvious directionality to his findings. When we started the industrial age in Europe, we were at 280 in 1750. So we started about here when we started burning coal. And look, this part was pretty slow because we didn't have a lot of coal and we didn't have a lot of Europe. Today, we're about there. apparently the top of Hawaii was like a really good place to measure it, and he found a lot. Now, does anybody notice that there's like a little zigzag pattern? This is number 19, and I'd like someone to explain this. Why does the Earth, quote unquote, breathe? Why does it go up and down every year?
Growth of like new plants and space.
Kind of, but how many of you say it's seasons? How many of you still say it's seasons when you consider that it's always the opposite season on the other half of the planet, but this is the whole atmosphere? But it is seasons. Anybody know the difference? But it's always summer somewhere, you know, the endless summer concept. Right now it's summer in Argentina. Yeah?
Like the Earth's rotation around the sun, it's not always equidistant from the sun.
Nope.
Rain.
What?
Rain.
It's always raining somewhere, yeah.
Is it because there's like way more some vegetation in one hemisphere than the
It's the opposite of that, but yes.
there's way less some vegetation in one hemisphere?
Which means there's more. Okay. Yes. Now comes the news flash, and this is totally noteworthy. The ocean does more photosynthesis than land. And the southern hemisphere has a lot more ocean. So the southern summer has more photosynthesis. So the southern summer eats up CO2. While the northern summer has a lot left over.
What comes after the southern hemisphere has more ocean?
So there's more photosynthesis in the southern hemisphere. So the southern hemisphere uses more CO2 in their summer. Southern hemisphere uses more CO2 in their summer. All right, anyway, that was number 19 that we just poked into. Now we're back to number 20. I want you to notice, please look up. That if you look 10,000 years into the past, all of the greenhouse gases have spiked in the last 50. That's 10,000 years of the atmosphere. Remember, ice cores trap air bubbles, little time capsules of the past atmosphere. In 10,000 years of ice core atmospheric time capsules, all of them have spiked in the last 50. Now, just to be clear, we're pretty confident that our Earth's atmosphere had high levels of these gases in the past at some point. That happens. But those levels never changed as quickly as they have recently. You have to get coffee right now? Other plans?
Yeah, I do.
That pattern would not be so interesting if it didn't perfectly explain our unnatural temperature spikes. Remember that nature alone cannot explain recent temperature trends. All of our knowledge of nature, which explains the past, cannot explain the last 50 years. But if you add those gases, it does. There is no mystery here. No mystery. And by the way, it's not like we don't have other data to correlate this. The amount of heat in the world's oceans, levels of sea level rise over 40 years, heat gain by the ocean and by land. The temperature in the Arctic over 2,000 years. Look, remember I told you that we've been entering a slow cooling trend? Except for, look, it correlates perfectly with the industrial age. Here's Arctic ice pack for the last 40 years. Here's Arctic ice mass going back 1,450 years. Look at the last 50. Here's the rate of melting in Greenland, never been faster than the present. Here's the volume of Greenland's ice. In the 4 years or 5 years since this graph was made, the graph turned deeply downward. Greenland is disappearing now. We know that the conveyor belt has slowed. We have these records, and by the way, we've correlated them with separate studies over and over. And now we have 12,000 years of records, and it's never been this high, it's never changed this quickly, and it's going up really far, really fast. Yeah?
So when Greenland melts, like let's say we just fix global warming, how would it gain mass again? Sea ice would just freeze and then collapse?
Yeah, there's winter, you know. So winter happens, and if winters are normal and they have a good long duration, the early part of winter cools the water, then it cools the land, then the snow starts to pile up, and then you keep getting more snow and more winter. All this is because winters are abbreviating. They just released a research paper on Thursday in Science that says the duration of ice pack in the Arctic has gone down by 5 days per decade for many decades. So after 5 decades of that, we've got almost a month less of ice pack. There it is. That's more time that the Earth has a lower albedo, so we're absorbing more heat. We're evaporating more water from the ocean, so there's more rain in the spring and the summer, which melts the snow faster. It's a positive feedback loop. And look, there's this question, right? Like, don't scientists have... isn't there like a debate somewhere? Whenever I look on the news, there's the guy that says no, right? You guys ever notice that? That on the news they always have the balanced reporting? That's kind of funny, actually. Because it's not really science that has any questions. You'd be hard-pressed to find a climatologist to tell you otherwise. I'm serious. You can try all you want. You find me one. They find a few. They're usually people that have low publication histories, that were not very respected in the field, that have since gotten massive donations from certain people who benefit from the doubt. But look, there have been these research papers that said, oh, no. There are some scientists. Well, when you say some scientists, that includes scientists from any field, like agricultural soil scientists and veterinarians and stuff. That's where the 11% came from. When you do a study of just the climatologists, you get less than 1%. There have been a lot of studies. By the way, you can just Google all this if you don't believe me. There's the name of the study. This is a really big one. Here's a couple of others. They found 97 out of 100. Here's the 8 largest international surveys of scientists done in the last 5 years. So 2007, 2008, 2009, 2010, 2011. You do international surveys of all climate scientists, And you ask slightly different questions, so you get slightly different results. But that's not a lot of doubt. Then you watch TV, and on the news, you'll notice that 72% of reporting includes a skeptic. And that's perfectly reflected by public opinion. If the news told you that there was significant skepticism about the earth being round, you might be skeptical too. You know what's funny? Being a skeptical is intelligent. If you're a skeptic, you're smart. You're thinking critically. Right on. Science is based on skepticism. That's the whole point of science. We don't make assumptions. We wait for the evidence. If somebody goes, the earth is round, I'm like, I don't know, it looks flat to me. Prove it. That's smart. That's being scientific. Right on. You go with that. But once everybody's convinced that people fabricate skepticism, we are lying to the public. I'm going to start a thing. I want to do my rabbit skeptical society. And anytime they put rabbits on the news, I'm going to complain, hey, fair and balanced reporting. We got skeptics. We don't believe in bunny rabbits. Anytime that the news says something about bunny rabbits, it's going to take a few $1 billion. Maybe I'll get some from Exxon. And then, whenever they mention bunny rabbits on TV, I'm going to go, wait, fair and balanced, fair and balanced. We have a scientist here that doesn't believe in bunny rabbits. You've got to put him on. There's a conflict of opinions. And the public's going to go, wait, there's doubt about bunny rabbits? All right. This is what we call fabricated doubt. It's a tool of propaganda. It's not the scientists that are skeptical. It's the public, because what the news is telling you to be skeptical of. But the basics are really, really, really simple. And you got to know these things. This is the whole rundown. This is man-made climate change, right there. You find me something wrong with this, I'll change my slideshow. I'm willing to be wrong. I'm skeptical. I have no attachment to being right. I like to be righter every day. So if I can be more accurate tomorrow, I'll feel good about myself. Whenever you hear somebody say they don't believe in climate science, say, well, okay, that's nice, but can you please show me empirically what's wrong with climate science? Where am I wrong here? Remember the dudes on the news that are skeptical? They got nothing to say about this. They're like, hey, it snowed yesterday in Tennessee. Yeah, so there you go. That's not like finding anything wrong with the science. It's misrepresenting a small part of the argument. It's like saying humans don't evolve. My mom's not a monkey. Well, I know your mom's not a monkey. It's not what evolution says, so great debate. So there's these gas molecules that wobble when they're heated, and then they give off the heat when they stabilize. They're called greenhouse gases. Back to normal. This allows some of the heat escaping the Earth to quote-unquote bounce back. It's not actually bouncing, it's being absorbed and then re-released. Some of it comes back downwards. That's the greenhouse effect. That's fact number 2. We are adding those gases, and you can measure that, and you can test those measurements, and you can make them. It's not that expensive. You can buy a test kit on the internet. When you go, you can measure it at home, but it'll be corrupted by your neighborhood. But if you get up to the top of the Sierras, you can measure the atmospheric levels of those gases. You can make your own research. Go right on ahead. Piece of cake. Highly corroborated. Easy data. We are adding to the levels of those gases. We know exactly how much. It's all been measured by like thousands of PhDs. And thus, we are adding more of the gases that trap the heat and put it back. In other words, we are heating the planet. Checkmate. We gotta have an honest debate about how we're gonna deal with it, how much we're worried about it, who's gonna pay. Totally necessary conversation, yes. But to believe or disbelieve a field of science is just not the right lingo. That's not how we deal with these issues. We learn it, and then we look at the facts, and then we can argue over the facts, and then we're getting smarter. To disbelieve in bunny rabbits cannot be logical. That cannot be a political platform. You cannot say, I disbelieve in bunny rabbits to get votes. That's just stupid. You certainly can't vote for a guy that doesn't believe in bunny rabbits. If they can say that with a straight face, somebody's got to be paying them a lot of money, right? Check it out. I got number 21 for you right here. You should try to copy some of this for number 21, and then whatever you cannot read, I will read to you. So don't ask me now. But copy the parts you can. I'll come back in about 1 minute to fill it in. Yeah.
What's the difference between N2O and nitrogen that's 70% of the atmosphere?
Nitrogen is an element. N2O is one of the compounds of nitrogen. Most of the compounds of nitrogen in our atmosphere are in other compounds, like N2, diatomic nitrogen, or nitrogen oxides, like NO2 and NO3. Very little of our atmosphere's nitrogen is in that compound. Answer your question?
Yeah.
Is that safe? Are you asking questions now?
No. All right. So watch me. I'm going to read all the things that are on the board. So if you don't follow me, I may not be able to answer your questions. The main greenhouse gases by volume are water, carbon dioxide, methane, nitrous oxide, ozone, and to a lesser degree, the fluorinated gases that I'll describe separately later. That means H2O, CO2, CH4, N2O, and O3. The fluorinated gases I'll describe later. Please look up. If you measure their effect, like the percentage of the total greenhouse, Water's 36 to 70. Carbon dioxide is 9 to 24. Methane is 4 to 9. Nitrous oxide, that's laughing gas, by the way, that's 2 to 5. Ozone is 3 to 7. And the fluorinated gases are 2 to 5%. Now, if you compare today's values to the year 1750, some of these gases haven't changed at all. Please look up. Water is the same as it was 265 years ago. In other words, humans aren't adding water. We've elevated CO2 by 50%, methane by 130, nitrous by 15 or 20, ozone by about 10. And all of the fluorinated gases are new. We've made all of them. They're entirely man-made.
Are those all 0.50 or
Oh, that is plus 50%.
the plus?
So, this is another way to think about these, and I hope you've been following, because those of you that have been distracted may be lost at this point. The majority of the greenhouse effect is water, but we're not adding it, so that has 0% of man-made warming. Does that make sense? The majority of the warming is water, but we don't add any, so that's not our fault, so that's not man-made warming. Of the heat contributed by humans, half comes from CO2, 20% from methane, 5% each, roughly, from nitrous and ozone, and a huge amount, 15 to 20%, comes from our fluorinated gases, the industrial gases that are all man-made. Most of our heating is from these little tiny smidges of the greenhouse effect. So let's talk about those. Anybody want to ask me a question on the table so far? This would be the right time. Yeah.
What does it still say about the third section?
Increase relative to 1750. Yeah. Increase about 10%. That says by volume. All right. Let's talk about fluorinated gases. Fluorine is a very strong bonder. Fluorine can hold many other atoms attached to it. Fluorine holds on very, very tightly. It just needs one more electron, and then it'll hold on to that electron like crazy. In other words, it can wobble really hard and it won't let go. So fluorine compounds can absorb a lot of energy, and eventually they will stabilize and give that heat back. Fluorinated gases are super greenhouse gases. They are strong bonders. They can bond with almost anything, and when they do, they hold on to that thing like crazy. Like I Jose when he finally got a girlfriend. He's like, oh my God, I'm never going to let her go. Never, no matter what. I don't care what she does. Like that. So, man-made fluorinated gases are super clean. They're really wobbly. This one, please look up, has 6 fluorines, sulfur hexafluoride. That one, you should write this down, 23,000 times hotter than CO2. This one, you can heat it up really, really, really hot. For those of you who speak chemistry and physics, fluorinated gases are used as coolants in heat exchangers, specifically because they can carry so much temperature. So these are like the stuff that makes your air conditioner work. They take away heat very well. VFC stands for fluorocarbon, so chlorofluorocarbon, hydrofluorocarbon, and perfluorocarbon. Halocarbons and sulfur hexafluoride. All man-made. Per molecule, they hold a lot of heat. So even though they're not big by volume, they are really big by the contribution to man-made global warming. Any questions about this? Because look, I'm almost out of time, but I wanted to show you something. This is the part where scientists do have a lot of disagreement. It's very hard to predict the future. Some people are optimistic, some are pessimistic, some believe in a factor more or less than other people believe in that factor, and predicting the future gets really tricky. But just so you know, our models have gotten better. We include more and more and more and more variables. We include different winds at different altitudes with the effect of chemistry in the atmosphere, secondary pollutants, interactions with land plants, interactions with the ocean cycling of gases. Our computers have gotten smarter, so we can break up the planet into millions of little pieces and keep track of all of them separately. And there is no graph which doesn't show significant global warming in the future. We can argue how much, but there's no graph that shows global cooling in the future. That doesn't exist. There's no scenario where our planet gets cooler. That has never been proposed by any credible study. You can change the variables, you can be optimistic or you can be pessimistic, but they all show some amount of heat gain. If we just froze CO2 14 years ago, we would still have warming. Of course, CO2 has grown, and it's grown by an increasing rate because China and India have many poor people, and those people are growing their energy use faster than the Western nations did with smaller populations. So there's more people at a faster rate of growth. CO2 emissions are not only going up, they're going up by an increasing rate. It's not just flat, and it's not just this, it's curved upward. Okay, that was the end. Bye-bye. I want to say yes, but I'm not smart. Yeah, oxygen, nitrogen, carbon, neon.